Distinguished members of the dais, colleagues, students, members of the public. We are gathered here to get a glimpse of one of the greatest adventures undertaken by mankind, to know and comprehend our universe from the largest cosmic scales to the smallest scales of elementary particles. And we are fortunate for the occurrence of this rare event at the Tata Institute, where four of those who have painted a significant part of the vast landscape of cosmology and elementary particle physics have gathered to tell us about our present knowledge of the universe. I extend my heartiest welcome to Professors Richard Bond, John Ellis, James Peebles and Kip Thorne, who are with us on the dais. The subject of these public lectures is one of the greatest triumphs of theory and experiment and represents work which is done over 4 to 5 decades. This event is part of a 3-week-long activity of the International Center for Theoretical Sciences of the Tata Institute in Cosmology and Gravitation, with an active involvement of the Department of Theoretical Physics, the Department of Astronomy and Astrophysics of our institute here, and of the IUCA in Pune. I would like to especially mention the names of Subhabrata Majumdar, Tarun Sauradeep, and T.P. Singh, who have worked very hard to put the whole program together. And with these few words, I would like to invite Professor Musnad Barma, Director TIFR, to address the audience.
Thank you. So this afternoon we have a very delectable fare for you. 4 public lectures, given by practitioners who are great experts in the field that they work in, and I'm sure all of you, this young audience, is in for a treat, in a few minutes. At TIFR, we take the idea of outreach, public outreach, rather seriously, and our program of public lectures, where we try to engage the public, and in particular the students of the city, with exciting developments in science. This is the forum in which we do this. I'm very happy to see a large number of students here today, and to them I wanted to say, you have your full lives in front of you, careers in front of you, and I'm sure you have some interest in science, otherwise you would not be here today. Science is a fantastic career option. Keep that in mind as you go ahead. And the thing about science that engages all of us, and I'm sure if you take this up, will engage you also, is that it keeps throwing up surprises. Small surprises and big surprises all the time. And this is something I think that you will see very much and very clearly this afternoon as you listen to these talks, and you see the connections between the very large and the very big scale phenomena at very, very large scales, namely the scale of the universe, and phenomena at very tiny scales, the scales of elementary particle physics. As Professor Wadia mentioned, this event happens under the aegis of the International Center for the Theoretical Sciences, but in fact involves several departments across the institute. Department of Theoretical Physics, Department of Astronomy and Astrophysics, and in this case also an institution from outside TIFR. And I'm very happy that this combination has this combined effort has actually resulted in a very fine program on cosmology, gravitation, and particle physics, which will happen over the next few weeks. So welcome, students. Once again, keep alive this engagement with science, and I hope to see you all much more often in future as well in this auditorium. Thank you.
Thank you, Mustansir. Now I'd like to invite Mustansir to give a bouquet of flowers and a memento from the Tata Institute to these distinguished speakers. So, Professor Kip Thorne. James Peebles. Richard Bond. And John Ellis. Let me invite Professor Sandeep Trivedi of the Tata Institute of Fundamental Research, Department of Theoretical Physics, to introduce a Caltech alumnus, Professor Kip Thorne. So I think now we all move down.
Yeah.
And we just begin.
To introduce our first speaker this afternoon, Professor Kip Thorne, who is the Feynman Professor Emeritus at the California Institute of Technology in the United States. In a career spanning over 50 years, Professor Thorne has made very significant contributions in the study of black holes, gravity waves, the astrophysics of relativistic stars, wormholes, and so on. And he is widely regarded as being one of the most distinguished theoretical physicists of our times, working in the areas of gravitation and astrophysics. Besides his own contributions, he has also mentored over 50 PhD students. Some of them have gone on to become major scientific figures in their own right. He is also well known to be a wonderful speaker and a wonderful teacher, so I'm sure we are all in for a great treat this afternoon. I've been asked to keep this introduction short, so I won't go on as I can, telling you about his many wonderful qualities, but I should add a few things. First of all, I can personally attest to his great teaching talents, because I was fortunate to take a course on gravitation from him when I was a graduate student at Caltech, based on a very famous book he has written on the subject, universally called MTW, which some of you might have seen. Otherwise, if you're interested, I encourage you to take a look at. And I want to mention two of his hobbies and then stop. Quite recently, he has become involved in producing a Hollywood movie. Living in Southern California for a while can do that to you. Engaged in producing a movie with Steven Spielberg, which we look forward to seeing. He has also had a long-standing fondness for gambling, having taken many famous bets with the likes of Stephen Hawking. Again, something you might have heard about. And again, this is a habit he used to try and inculcate among young impressionable minds who took his courses. So, with those few words, let me invite Professor
today about what I would like to call the warped side of our universe. By this I mean objects and phenomena that are not made of matter like you and I, but that are made instead of warped space and time. The prototypical example of this is a black hole. A black hole, as you all know, is something that has a roughly spherical shape down which you can fall, and if you fall in, you never can come out. But in fact, the black hole is much more interesting than that, as I shall describe. It is actually made from warped space and time. The matter of the star that imploded to form the black hole long ago has long since been destroyed at the center of the black hole, and all that is left is warped space and time. You can understand this by an analogy. Let's take a rubber sheet, a child's trampoline, put it up on tall stilts, and put a very dense rock at the center so it bends the rubber down in the manner that I've shown here. Now imagine you're an ant, an insect, and you live on this rubber sheet, and you have studied at the TIFR, and so you know all about geometry. And so you decide that you're going to measure the geometry of your universe. You go marching around and you measure a circumference, and then you measure a diameter, and you discover the diameter is much larger than the circumference. And you say to yourself, obviously that means I live in a warped universe. It's a warped because this does not obey the geometry of Euclid. And precisely the same diagram can be used for a black hole. All I do is change the labels. The space in which you and I are living, looking in from the outside, I like to call hyperspace, or sometimes people would call it the bulk, a concept that is used in string theory. A hyper being, or a bulk being, looking in from outside our universe would see it look like this in the vicinity of a black hole, with the geometry bent down like that, so circumferences are small compared to diameters. At the center, the rock is replaced by something called a singularity, which I will talk about. And the black hole does have this property, that if I fall in to the black hole, trying to send signals out with a microwave transmitter as I fall, there's a location called the horizon, beyond which both I and the signals get pulled down and destroyed in the singularity. I pay the ultimate price of going inside the black hole that I cannot publish the results of my studies. And so the signals and I get pulled in, and the horizon then is the point of no return. The horizon, as I shall explain, results from the warping of time. I'll explain that in a moment. So the black hole has the warping of space that I've described here. It also has the warping of time. Time slows as you move down near the horizon, so that if you were to go close to the horizon, stay there for a few hours, then return to Earth, 1 million years might have passed on Earth. If you go below the horizon, time becomes even more weird. Time now moves in a direction that you might have thought was a space direction toward the singularity. And that's why nothing can never get out, because nothing can move backward in time, at least locally. And so nothing can get out of the black hole, because in order to get out, it would have to move backward in time. The black hole also drags space into a whirling motion. We call this the dragging of inertial frames. With an angular velocity proportional to the length of that arrow, a large angular velocity near the horizon, and a much smaller angular velocity farther away, very much like the air in a tornado. Now, a black hole is just one example of phenomena that we believe may exist on the warp side of the universe. Another is the Big Bang singularity, in which things are not destroyed, but rather the universe was created, emerging from the Big Bang. There might be naked singularities, where everything gets destroyed because gravity is so strong it tears things apart. Singularities that do not reside inside a black hole, that are not hidden from the exterior by a horizon. We don't know. I'll return to that briefly near the end of the lecture. Our universe may actually be a three-dimensional surface living in a higher dimensional space, a brain living in the bulk. These are ideas that come from modern string theory. There may be huge strings that stretch across the universe called cosmic strings that have a warped space around them. The circumference around the string is a little less than pi times the diameter. And there are almost certainly gravitational waves, waves that are made of ripples in the surface or in the geometry of space-time, ripples that travel outward, of warping of space and slowing of time, travel outward from their source to Earth, bringing pictures of their sources. So the question is, which of these phenomena on the warp side are real, and what other kinds of phenomena are there on the warp side? To answer this question, we have a set of tools. First, we have theories epitomized by Hawking here and Einstein there, working with equations directly on a sheet of paper or in a computer analytically. We have numerical simulations, a new tool that I will be describing to you that we've never had until the last several years. We have optical, radio, and other electromagnetic telescopes with which we look at the sky. And then we have gravitational waves, which are really the ideal form of radiation to study the warp side observationally, because they are made of the same thing as phenomena on the warp side. They're made of warped space and time. And we have gravitational wave detectors in existence and planned for the future. And I will be talking today primarily about numerical simulations and gravitational waves. These are new tools which are today in the process of opening up our understanding of the warp side of the universe. Now I'm going to be talking for a little while about collisions of black holes, and I'll explain why. These are really a phenomenon on the warp side that we did not understand at all until very recently, and now we are beginning to understand that these have a very rich set of phenomena related to how warp space-time can behave. The basic idea is that two black holes orbit around each other, spiral together, and merge, and in the process they generate gravitational waves that come traveling out to Earth, bringing a detailed picture of what was going on with warp space-time as these black holes collided and merged. Now it's rather startling when I tell you some numbers. The total power output in gravitational waves during this collision and merger is 10,000 times the luminosity of all the stars in the universe put together. 10,000 universe luminosities of energy, of power coming out during that merger. If the black holes are small, the merger doesn't last very long. If they're large, it lasts a lot longer. So for large black holes, you get out more total energy than for small ones. And no electromagnetic waves are emitted whatsoever. This power is all in gravitational waves, except that if you have a disk of hot matter around this binary black hole system, as the gravitational waves go out, they will disturb the disk, and there should be interesting electromagnetic phenomena to be seen with optical radio gamma ray telescopes. The gravitational waves have a shape. They have a waveform like the waveform you see on an oscilloscope for sound. The details of that shape are the things that encode the details of the collision and how warp space-time was behaving. And so what we want to do is detect those gravitational waves, measure the waveforms, and from the waveforms extract the details of how warp space-time behaves in this highly unusual situation. Now, why are black holes interesting? To me, they're particularly interesting because each black hole drags space into a whirling motion, so it's like a tornado. So a binary black hole system is two tornadoes orbiting around each other. The orbital angular momentum also drags space into motion. So it's two tornadoes embedded in a third larger tornado, and they come crashing together, and they excite some wild behavior of warp space-time that we want to understand, both theoretically and observationally. Our tool for understanding this theoretically is numerical simulations on giant computer clusters. I'm going to be describing simulations carried out by a group I'm associated with at Caltech, Cornell, and the Canadian Institute for Theoretical Astrophysics. These people are the key players in this work. I'm going to first show you a movie. The first movie that our collaboration was produced the details made by Harold Fiver, who's now at CETA and was at Caltech at the time in my own group. And this movie shows then the collision of these two, orbital motion and collision of these two black holes. Now you're going to see the black holes up in the top against a dark blue sky. You see them as black spheres. This is what they would look like if we saw them in our own universe. In the central region here, you see the black holes viewed in terms of the warped space and time. The shape of this funnel is the shape of space, as seen by a bulk being looking in from the bulk or looking in from hyperspace. The colors show the slowing of time as you near the horizon of the black hole. And the arrows show the dragging of space into motion by the orbital motion of the black hole. Now these black holes are not spinning, so there's no whirl of those arrows around the black holes. But space is dragged into motion nevertheless in interesting ways as shown by these arrows. Down at the bottom you see the gravitational waveform. A very simple waveform because this is a simple situation. Identical black holes, neither of them spinning, coming together in a circular orbit. So a very, very simple waveform. Now, this orbital motion you see now in the two black holes seen looking in from the bulk, as seen in our universe. Here we are in the gravitational waveform. This gets boring after a while, so we're going to jump from here over to here, and then watch the black holes merge, and we'll pause the movie as the black holes merge so you can admire it. And then the black holes, merged black hole vibrates and begins to settle down into a final state. The tools of research to do this required some 40 years to develop. It was a very, very tough thing to be able to simulate Einstein's equations on computers and get out movies such as this and the detailed gravitational wave shapes that come off. In just the last year and a half, we have understood much more about the richness of this phenomenon of the black holes and their collisions. And a key to this is understanding in better detail the whirling motion of space around a black hole, a spinning black hole. We have learned that there are things we call vortex lines or frame drag vortex lines sticking out of the black hole. These vortex lines can be thought of as guiding the whirling motion of space. Now, the whirling motion of space is stronger near the black hole than farther away, and so if I put a person here and she looks down at her feet, she sees a gyroscope at her feet dragged around relative to her head. It's dragging around faster than her gyroscope at her head, so she sees this going in a counterclockwise direction. If you look up from her feet to her head, and her feet see a gyroscope at her head going counterclockwise. And so these vortex lines describe a counterclockwise twist of space, very much like wringing a towel. If you have a wet towel and you wring it to get the water out of it in a counterclockwise direction. That's what's going on with space here. In the southern region, there are vortex lines that describe a clockwise twist, the opposite kind of twist. So there are two sets of vortex lines. We call this a vortex, a collection of vortex lines that describe strong twisting of space. So there are two vortexes sticking out of this black hole. Now, this is a subject that is new, and even experts on relativity theory don't know what this is about. So for those experts, I'm going to tell you very briefly. We are looking at these vortex lines are integral curves of the eigenvectors of the magnetic part of the vacuum Riemann tensor. Now, for everybody else, that's gobbledygook. But the key thing is that these are concepts analogous to magnetic field lines that are so useful in describing magnetism. And they are becoming a very useful tool for understanding space-time curvature. Suppose that I have two black holes. They're spinning in opposite directions. So there's a counterclockwise vortex up here and a clockwise vortex there. They're going to collide head-on. I'm going to show you a movie of this. When they collide head-on, it turns out that they will deposit onto the horizon. What you're seeing here colored is the horizon of the black hole. The blue region is where a clockwise vortex is sticking out. The red region is where there's a counterclockwise vortex sticking out. And the black hole horizons have merged. We now have a single black hole. And the vortexes have retained their own identities. They still exist as independent entities. And the movie now is going to show you what happens. I won't show you the lines. I'll just show you the color coding for what kind of line is sticking through the horizon in this movie. So if you watch, now, I'm going to back it up. You see the black holes raise a tide on each other. And the tides reach out and grab hold of each other. You now have a single black hole. This is the black hole horizon. This is the point of no return. You fall in and you can never get out. And now, remember that on your right, you see a blue vortex on the top. That's a clockwise vortex. On the left, there's a red one. And watch what happens now. The black hole vibrates. And the direction of twist flips back and forth. It's really interesting. We just discovered this in the simulations recently. That these vortexes discover the presence of each other. And they basically exchange their vorticity. They change the direction of twist. And so they slosh back and forth in the direction of twist. And every time this thing is totally green, there are no vortex lines sticking through. And so those vortex lines have come off temporarily. And they reconnect and go flying away from the merged black hole. And this is the pattern that comes out of the computer simulations. This is direct off the computer simulations. You get basically something like a smoke ring of twisting space coming. This one came off quite some time ago. This came off in the next previous oscillation. And these are getting ready to form a vortex ring and come flying off. And these vortexes, as they come flying off, they become the gravitational waves whose detection I will be describing in a few minutes. More interesting astrophysically is the case where these black holes are orbiting around each other and they're going to collide. I won't show you a movie in this case, I'm just going to show you what happens. That as these black holes merge and collide, again you have the 4 vortexes sticking out. And those vortexes form spiral arms now as the merged black hole rotates. Turns out there are 2 more vortexes, one coming out toward us and one going into the screen. They're associated with the rotation of the black hole. These 4 vortexes that came from the individual black hole spins now sweep back in spiral arms, reaching out and becoming gravitational waves that we want to detect. This dragging of space into motion is really very strong, and I'm going to illustrate this by another simulation in which we have a black hole that weighs 3 times what this star weighs. This is a neutron star made of pure nuclear matter, and matter that actually gets up to 10 times the density of an atomic nucleus in the center. This black hole might weigh about 5 solar masses, 5 times the mass of the sun, and the neutron star about 1/3 of that. The neutron star is orbiting around the black hole in this horizontal plane, and it's going to be torn apart by the black hole, and all of its matter is going to be thrown up into the plane perpendicular to the black hole's spin by this vortex motion caused by the vortexes that stick out of that black hole. So here is the simulation. The neutron star is already being thrown up into the other plane. It's now being torn apart. And matter is spewed out and around and forms a disk, a hot disk of matter around the black hole. This is nuclear matter that has been opened up for all the world to see, extremely hot. It's emitting gamma rays, it's emitting neutrinos, and as it cools, it will emit, continue for some time to emit optical radiation and radio radiation. As the star was torn apart, it was emitting very strong gravitational waves. And so what we want to do in the next few years is open the new gravitational wave window onto the universe and simultaneously observe this kind of a phenomenon using multimessenger astronomy, the messengers being gamma rays, neutrinos, light, and radio waves, for example, and other forms of radiation. So let me turn my attention for the remainder of my talk to the challenge of detecting gravitational waves. Electromagnetic and gravitational waves, though 2 kinds of radiation, are very different from each other. Electromagnetic waves, physically, they are oscillations of the electric and magnetic fields that propagate through space-time. Gravitational waves are oscillations of the fabric of space-time itself. They're oscillations of warping, rather like the oscillations of the undulations on the surface of the ocean when an ocean wave goes by. Electromagnetic waves are almost always, in astrophysics, incoherent superpositions of the emission from individual particles and atoms and molecules. Gravitational waves are emitted coherently by the bulk motion of matter or the bulk dynamical oscillations of warped space-time in the case of an object like a black hole. Electromagnetic waves are very easily absorbed and scattered, and so it's very difficult to see into the center of the galaxy. You can't do it with ordinary optical light. You can do it with infrared light because of the absorption and scattering. Gravitational waves are never significantly absorbed or scattered. Even gravitational waves produced in the Big Bang that have to travel out through the very hot matter in the early universe, not at all absorbed or scattered. And so these are very different kinds of radiation. And that means that the gravitational wave window on the universe is going to be radically different from our current electromagnetic windows. And as a result, it's very likely that we will have enormous surprises brought to us by gravitational waves and by the joint observations of gravitational waves and the other messengers of astronomy. There are actually 4 frequency bands and 4 different kinds of detectors that are going to open up the gravitational wave window onto the universe in the next roughly 10 years. I will be talking primarily about the high frequency band of 10 hertz to 10 to the 4 hertz, 10,000 hertz. And this is the band in which Earth-based gravitational wave detectors operate, things called LIGO and Virgo and Einstein. The low frequency band I'll say a little bit about. This requires space-based detectors, spacecraft that track each other with laser beams. As the gravitational wave goes by, they're moved back and forth relative to each other, and the laser metrology tells you about that motion. They operate in the low frequency band between 1/10 of a hertz and 1/100,000th of a hertz. That is periods between a minute roughly and many hours. The very low frequency band pulsar timing by radio telescopes is likely to open up the observations onto the universe. I don't have time to discuss this, but I will only say that there is a race on today between pulsar timing and the Earth-based gravity wave detectors as to which will detect gravitational waves first. The Earth-based ones will see gravitational waves with masses from black holes that have masses of a few times the mass of the sun, up to 1,000 solar masses. This technique, using radio observations of pulsars, will look at black holes that have masses from 10 million solar masses to 10 billion solar masses, so enormously massive black holes. And then there's observations of the anisotropy of the cosmic microwave background radiation, which will tell us about waves that have wavelengths, that have frequencies that are of order the age of the universe, wavelengths of order the size of the universe. I won't go into this either, but this is a very exciting prospect for observing the birth of the universe with gravitational waves. So let me talk about gravitational wave detectors here on Earth, operating in the high frequency band. This is a theorist's simple picture of how one works. You have 4 mirrors that hang from overhead supports. When a gravitational wave comes by, it pushes these mirrors apart when it's pushing these mirrors together. And then a half a cycle of the wave later, it pushes these apart when it pushes these together. So it's a stretching and squeezing of space, but it's a very tiny stretching and squeezing, which is monitored using a technique called laser interferometry, which I will not go into in any detail. The bottom line is that the separation changes between these mirrors by an amount that is proportional to their original separation and proportional to the gravitational wave field. This gravitational wave field is dimensionless. The arm lengths that we have for the LIGO gravity wave detectors that I'll be talking about are about 4 kilometers. The strength of the waves that we expect to be seeing, according to astrophysical estimates, are less than or of order 10 to the minus 21. That product is 4 times 10 to the minus 16 centimeters. So the challenge is to measure the motion of mirrors that are separated by a distance of 4 kilometers. When those motions are 4 times 10 to the minus 16 centimeters, you need to get down, because you have to deal with noise, to at least 1 times 10 to the minus 16 centimeters. That is where currently operating instruments are. Let me just remind you of what this means. Even for a physicist of my age and experience, it's really salubrious. It's really educational to remind yourself of what I'm going to show you. So here is 1 centimeter on the screen. Divide by a factor of 100, you get the thickness of a human hair, about 100 microns. Divide by another factor of 100, you get the wavelength of light that is being used to make these measurements. Divide by 10,000, you get the diameter of the nucleus of the diameter of an atom. Divided by 100,000, you get the diameter of the nucleus of the atom down to the center of the atom. Divide by 1,000, and you get the strength of the gravitational waves action on these mirrors. I wrote a textbook that Sandy referred to in introducing me, MTW. In the textbook, when I wrote this in 1971, there's an exercise for the reader. The exercise is to show that it is ludicrous. It's crazy to think you could ever detect gravitational waves of this kind of a magnitude using the technique of laser interferometry. Well, I was wrong. And beginning about 9 years after I wrote that, from then until now, I've devoted a large fraction of my career to helping make this happen. So it just shows how wrong one can be. The Earth-based gravitational wave interferometers, as I said, go after black holes with masses between 10 and 1,000 solar masses. They have sizes, these black holes, between 10 kilometers and 1,000 kilometers in size. So they're small objects, astrophysically speaking. There has been a network of gravity wave interferometers operated for several years. It consists of interferometers in Hanford, Washington, and Livingston, Louisiana in North America, in Hanover, Germany, and in Pisa, Italy. These green ones, these three make up the LIGO detection system, and then there's the Virgo project, which is a French, Italian, Dutch collaboration. We are hoping very much that within the next several years there will be built a detector in Japan called LCGT, and one in India that will be part of the LIGO collaboration. So I'm going to describe LIGO-India to you briefly near the end of the talk. Why so many detectors spread over the Earth? Because you can imagine that you're trying to measure this exquisitely small motions, and there's going to be a lot of noise in here you don't understand. So in order to be sure that you're really seeing a gravitational wave, you need to see the same kind of signal in a number of different detectors at different locations on the Earth. So for detection confidence. In order to extract the shapes of the gravitational waves, we need to you have to extract the shapes and the direction of the source simultaneously. Let me go to the direction of the source. We get the direction of the source by triangulation, that is, by the light travel time between Hanford, Washington, say, and Bangalore, India. If a piece of the signal arrives in Bangalore, but earlier than in Hanford, we know that the direction of the source is out in the Bangalore direction of the universe, and that this is the opposite direction on the sky. So we triangulate by time delay, and then having determined the direction of the source, we can get out quite accurately the shape of the waveform. And the waveforms, as I remind you, carry us with them in their shapes, encoded in their shapes, the details of how the dynamical behavior is going on in the warp side of the universe. The vortexes, for example, of black holes and what they are doing when black holes collide. LIGO is a collaboration of about 800 scientists at 75 institutions in 13 nations, and India has been a major player in LIGO for some years, particularly in the data analysis with a group of Sanjay Durandar at IUCAA. LIGO has, as its primary instruments at the present time, 2 in Hanford, Washington, in this vacuum system, and 1 in Livingston, Louisiana. We want to move one of the detectors that's in Hanford to India, and I will explain why in a few minutes. In 1989, when my colleagues and I proposed building LIGO to NSF and got approval ultimately to build LIGO, we proposed a 2-step strategy. We will build an initial set of interferometers in LIGO at a level of sensitivity where it's plausible but not likely for us to see gravitational waves. Then, having gotten our feet wet, had the experience, found where the problems are, surmounted those problems, we were ready to build the detectors or the advanced interferometers that we would have liked to have built in the first place. At a sensitivity where we are quite sure we are going to see large amounts of gravitational waves coming from many different kinds of sources. So, in fact, we built the initial interferometers and we operated them over the period 2005 to 2010. And we were able to look for black holes out to distances of about 300 million light years into the universe. We have not seen anything in our data as yet, but we are continuing to analyze the data. The data is still fairly fresh. The most recent, we shut down in October 2010 in order to begin installing our advanced interferometers, which are much more sophisticated, much more delicate, much more complex. Our advanced interferometers will begin their gravitational wave searches around 2014 or 15. They should be nearing design sensitivity by 2017, and I would predict we will see gravitational waves somewhere a little before 2017, but we will find out. And LIGO-India, if it goes online, if it's approved and funded and built, it will be nearing design sensitivity around 2020 and become a part of this network of gravitational wave detectors. This detection system, advanced LIGO, will see black holes colliding out to 4 billion light years at a rate of 3 per day collisions to 1 per year. The most pessimistic estimates anyone gives is about 3 per year. I'm sorry, this should be 3 per day and 1 per year. So I've got that. I've written it around. between 3 per day and 1 per year. But it will also see many other sources: colliding neutron stars, spinning neutron stars, low-mass X-ray binaries, perhaps cosmic strings. So there's a great richness of science to be done with these instruments. Now the experimental challenge is really considerable, and I can describe that by telling you that we have to monitor the motions of 40-kilogram mirrors to a precision of about 10 to the minus 17 centimeters, which turns out to be, in technical terms, the half-width of the Schrodinger wave function of the center of mass degree of freedom of the mirror. In non-technical terms, this is the accuracy at which we begin to see a 40-kilogram object behave according to the laws of quantum mechanics and not the laws of classical physics. So for the first time, human beings in LIGO will see human-scale objects, 40-kilogram objects, behave quantum mechanically with uncertainties in their positions and momenta that are governed by the uncertainty principle. And in order to deal with this, it has been necessary to design into advanced LIGO something called quantum non-demolition technology, so that the gravity wave signal, when it goes through these mirrors, does not get demolished by the mirror's quantum mechanical behavior. This is a branch of quantum information science, one of the most exciting new areas of technology for the 21st century. Multimessenger astronomy will be a major piece of the LIGO gravitational wave program. In preparation for that, at Palomar Mountain, where we have our 200-inch telescope, there has been built under the leadership of Sri Kulkarni, who's a professor at Caltech who came to us from India. There's been built something called the Palomar Transient Factory, wanting to characterize those phenomena in the sky where something suddenly gets bright and then dies out, transient phenomena, some of which will be gravitational wave sources, some of which will not. And so this is part of the planning for LIGO. What happens is a 48-inch Discovery telescope that sees a pretty big patch on the sky, sees something suddenly flare. It sends a signal to a 60-inch telescope that looks much more deeply and studies in detail what's going on with this source. And then, if it really is an interesting source, the signal information is sent to the 200-inch telescope on Palomar Mountain and other telescopes around the world to characterize in detail that source. And so in this way, the sky is being understood in the electromagnetic spectrum, at least in the optical spectrum, what's going on in transient phenomena, sudden changing phenomena. For multimessenger astronomy, a very important player is likely to be the giant meter wave radio telescope, which is based here at the TIFR, part of the TIFR. It's located 80 kilometers north of Pune, and it is likely to be the premier instrument for looking at the transient phenomena in radio waves that come from our gravitational wave sources. Now we have the problem that if we look at gravitational waves, we have to be able to tell the radio astronomers and the optical astronomers where to look on the sky, where it is that the sources that we're going after is located. So we need to be able to say, we saw something up here, we think it's two black holes that are merging. We saw something up there at a particular time, we think that it is a black hole tearing a star apart. And we do not have adequate angular resolution on the sky to be able to tell the electromagnetic astronomers where this source is until we get LIGO-India. Without LIGO-India, we're in trouble. So let me tell you about LIGO-India then. The proposal is to put one of the 3 LIGO advanced interferometers in India. Originally, we were planning to put all 3 in the US. We want to take one of them and put it in India instead. The USA would provide the interferometer components. They're identical to the components of the 2 advanced interferometers that are going in the United States. India would provide the infrastructure, sites, roads, buildings, vacuum system, the installation and commissioning of the interferometers with a lot of help from the international LIGO team, the operating costs, and this would build on India's extensive past and current role in LIGO data analysis. Plus, there have been a rather large number of young Indian physicists who have been trained in LIGO at various LIGO centers around the world who would come back to India to participate in this. The cost is there by a 5-year period. The benefits are to be a lead player in gravitational wave astronomy and multimessenger astronomy almost from the beginning, and spin-offs of some of the most advanced measurement technology that humans have, including the technology for extracting extremely weak signals from noise, optical interferometry, quantum non-demolition, and so forth. So those are the benefits to India. The benefits to the gravitational wave community in the world are indicated here. Here are error boxes on the sky for localizing the gravitational waves from 2 neutron stars that spiral together, collide, and merge without India. You see these long error boxes, really much too long for this to be very practical to tell an optical astronomer where to turn a telescope to look for this. With LIGO-India, these error boxes are vastly shortened, and suddenly it becomes very practical for the optical astronomers to participate with us in this business. The north-south uncertainty is greatly reduced with LIGO-India. If the Japanese also build an instrument there, it turns out they greatly reduce our error boxes in the east-west direction. So there's a real complementarity between the 2 new instruments that we want to bring into the international network. The average improvement in angular resolution is a factor of about 3.5. We would go for, say, for half of the sky, the best half of the sky, we would have angular resolution of at least 28 square degrees everywhere on half of the sky. With the only LIGO and Virgo, without LIGO-India, that gets reduced to 8 square degrees, and that's a huge reduction, and especially important in terms of reducing it so the error boxes are no longer so extremely long and thin. That's really what's needed to bring in optical astronomy. Well, I'm going to wind up with a few words about other things besides in gravitational waves, besides these ground-based interferometers. LISA, the laser interferometer space antenna, operating in the low frequency band, will go after gravitational waves from giant black holes in distant galaxies with masses between 10,000 and 10 million solar masses. That is, they have basically the same size as LISA, which has 5 million kilometer arms, spacecraft tracking each other with laser beams. There is a test flight to test the technology for this called the LISA Pathfinder test, which will fly in 2014, and if that goes well, LISA could be launched as early as 2022. As an example of what LISA can do in space, it can map with exquisite detail the warp space-time of a quiescent black hole. If I have a small black hole spiraling around and orbiting into a large black hole, it emits gravitational waves that carry a detailed map, a highly detailed map of the space-time geometry of the large hole that's being explored by the small hole as it spirals in. And we will extract those maps with LISA and study then in great detail the space-time geometry of massive objects around which small black holes orbit. And what if the map that we find is not that of a black hole? Suppose the space-time geometry is something else. Well, this is an example of the kinds of surprises we might have. We may have discovered a new type of inhabitant of the warp side of the universe. 2 long-shot possibilities are dense objects made from cold, dark matter, and naked singularities, which I mentioned to you, a singularity that is not hidden inside a black hole. Let me wind up by talking about what I regard as the holy grail for this field over the next 40 years, and that is to observe and study the first 1 second of the life of the universe. If we look out on the sky, we see cosmic microwave photons coming from all directions, and they bring us a picture of what the universe was like when the age of the universe was roughly 100,000 years. Well, 380,000 years. What's the factor of 3 or 4 to an astronomer? Roughly 100,000 years. And earlier than that, the universe was so hot and so dense that photons could not propagate. They were absorbed and scattered and lost all their information. Neutrinos, if we could see them coming from the very early universe, would bring us a picture of what it looked like at age 1 second. Gravitational waves, as I said before, are the only form of radiation that can come from the Big Bang itself, unscathed by interaction with matter. And so they are our only direct tool for directly observing what goes on in the first 1 second of the universe. And I'm going to give you 4 examples of the rich violence that might occur in the first 1 second of the universe's life. The first example is the Big Bang singularity and the very brief epoch that is called the inflationary epoch right after the Big Bang singularity, in which the universe basically was converted into a form that more or less begins to resemble the universe that we now live in. You'll hear probably a lot more about inflation later on this afternoon. There are these things called cosmic strings that I mentioned that may have been born in the Big Bang. These cosmic strings may stretch across the universe. When 2 cosmic strings run into each other and cross, they have a high probability to reconnect, and you wind up with a bend in the string. That bend then travels down the string at the speed of light, emitting gravitational waves. And so this is a simulation by Ken Olem at Tufts University with the gravitational wave being thrown off. The birth of the fundamental forces. When the universe was about 10 to the minus 12 seconds old, and its temperature in elementary particle physicists' language was 1 TeV. At that point, the electromagnetic force and the weak force are believed to have come apart, giving rise to, previously they were married in something called the electroweak force. They're believed to have come apart and then gained their own individual identities. This may have occurred in what's called a first order phase transition, so that you have a bubble of space where the forces live separately in a bulk around here where the forces are unified. When those bubbles condense like water droplets in a sky, they expand outward, collide, and emit bursts of gravitational waves as they collide. And those waves are then redshifted into Lisa's frequency domain. And if there is any kind of similar phenomenon, when the universe had a temperature of 10 to the 5 TeV and an age of 10 to the minus 22 seconds, the resulting waves would be seen by LIGO. So here is a far out possibility even for LIGO. And finally, our universe may in fact be a brain that lives in a higher dimensional hyperspace. And if that brain formed wrinkled like this, then when the adjacent parts of our universe, viewed as this wrinkled surface, discover the wrinkle between them, because of a great tension in that brain, they stretch out and the universe begins to vibrate and tries to straighten out like a drumhead vibration, and settles down then into its current form. And all the energy of vibration we see is gravitational waves. This is another example of the kind of big surprise that gravitational waves may bring to us. So in conclusion, we really are still extremely ignorant about the warp side of the universe. Questions we want to know: does a black hole have the precise shapes of warping that general relativity predicts? What happens when black holes collide? The Big Bang singularity, what are its details? What came before? Is our universe truly a brain in hyperspace? What other objects reside on the warp side of our universe? Singularities, what are their structures, their behaviors? The Big Bang singularity, the singularity in the core of a black hole. The answers will come from gravitational wave and multimessenger observations, and from theory and numerical simulations. Thank you.
Thank you, Professor Thorne, for a wonderful lecture. We have exactly 5 minutes to take a few questions.
When you talk about the shape of a black hole, you say spherical, but it bends inside, right? Wouldn't it be 4-dimensional? When you talk about the shape of a black hole, it's spherical, yet it bends within itself. So wouldn't it be 4-dimensional within 3-dimension space?
Okay, so the surface of a black hole is 2-dimensional. It's approximately spherical. The shape of the space of the black hole that lives in is a piece of our universe, so that's 3-dimensional. But in order to visualize it being warped, as we do, you have to look in from a higher dimensional space, a fourth dimension, in order to see that warping. That higher dimensional space that you look in from, it's not part of our universe. Our universe is confined to the 3 dimensions that we can experience. However, something in that higher dimensional space could interact with us. And I invite you to see the movie that I'm working on in Hollywood, where there are such interactions. This is obviously fiction.
Sir, you showed the simulation of when 2 spinning black holes collide, there is the oscillation of those vortex lines. Sir, is there the possibility of detecting them only by gravitational waves, or any other means can be developed to detect?
So the vortex lines, or vortexes of twisting space, they become gravitational waves as they travel out, so this is the primary way to detect them. However, they also will interact with any matter that's in the vicinity. For example, they will interact with a disk of hot gas that may be orbiting around those binary black holes and distort the disk and produce electromagnetic emission. But that's going to be a very messy process. It will be interesting. It will tell us something more about what's going on. But if we want to understand the vortexes themselves, I think only the gravitational waves will have the highly detailed information about what they're doing.
From there, it will also be possible to detect those oscillations you were showing when 2 spinning black holes collide.
Pardon?
Those oscillations of the vortex lines when 2 spinning black holes collide, those will also be observed from there only.
Yes, that's right. So that's right. That's our primary way to observe them. Let me remark, I didn't talk about it, but there is another set of lines sticking out of the black hole called Tendex lines that stretch and squeeze space. And they also produce gravitational waves by their dynamical motions. So Tendex lines are similar to electric field lines. Vortex lines are similar to magnetic field lines. And that is the entire story of space-time curvature, it turns out. If you can understand these Tendex lines and the vortex lines, you know everything about the space-time curvature of a black hole. So that's our goal, is to learn everything there is to know about how the space-time curvature is behaving through studying the waves produced by the dynamics of the vortex lines and Tendex lines.
So,
Last question.
is there a thing called vacuum actually in the universe, or does it also contain gravitational waves?
So others may talk about vacuum, I don't know. But in modern physics, the vacuum is very rich. You remove everything that you possibly can remove, and there still are fluctuations of everything that could exist. There's a little bit of fluctuation of electric fields, magnetic fields, and gravitational waves are always present in the vacuum. And so understanding that vacuum in detail is a major piece of modern theoretical physics.
As you said,
Just a minute. I think you can discuss outside during tea time. So we will end this lecture with another round of applause to Professor. I'd like to now invite Professor Tarun Saurali of IUCAA to introduce Professor James Peebles. Tarun.